Okay, this is going to be a little different. This is effectively cosmology with an 8-inch telescope. This is work that I led equally with Mark Postman and in collaboration with the New Horizons science team. New Horizons was a NASA probe that provided the first reconnaissance of Pluto, and Arrokoth after that, and it's leaving the solar system for interstellar space, and you can do a little astrophysics with it. So the question of doing the optical background can be framed by a simpler question, which is this: how dark is space? And this is asking, what is the integral of all optical light? And in measuring that, do you understand where it comes from? Is it entirely produced by all the galaxies you know? If not, are the galaxy counts incomplete? Is there stuff outside the galaxies, or is there some novel phenomenon that is generating light that you're unaware of? So our role is not to argue about the particulars of galaxy formation, but to set a lid and say, this is how much light you have to make, you can't exceed that. So this is an old problem that has gone back certainly to the 70s, if not earlier, and there are three ways to do it. The first way is to say, look, I think I know everything that's there, add up all the galaxies, do an exacting census, and that's the bottom line there, and that's been done a number of times, and the works I cite there are by Simon Driver and Saldana Lopez, which involves Joel as well, and I think a large crew of people with Santa Cruz. And the intensity is this obscure units, nanowatts per meter squared per steradian. But you see it's down here, and I've given a lot of room for other results. So this is what you infer from galaxies. And I should say the galaxy counts done by different people agree quite well. Another way to do it is to use, and this is a little obscure, to look at the intensity of very high energy gamma rays coming from distant laser sources. Very high energy gamma rays of a tera-electron volt or so cannot propagate through empty space if there are optical photons around. They will hit an optical photon, create electron-positron pairs, and be extincted. And that's an effect we see. So you can use that extinction to infer the optical background. If you assume that the overall shape of the optical background matches the galaxies, if not its intensity, you get the intensity quite nicely, and those are the colored bands done by a number of people. If you relax it, however, say, let's just let the optical background do anything, you are poorly constrained. And I should say these are the state of play of about 4 years ago. But the real thing is, if there's optical light, and if there's a background, you should be able to see it directly. And that has been disappointing, has been attempted by many people in many different ways over the last several decades, and none of the results detected the existence of the background at anything better than 2 sigma significance. So direct detection has not worked quite well. And the reason is because effectively in doing optical background observations on Earth or even around Earth, it's like doing optical astronomy in the middle of a bright city. You have very strong zodiacal light. We actually live in a very dusty place, and you can see zodiacal light, and it completely overwhelms the expected level of the optical background. And you can do a number of very clever things to get rid of it, and people have tried this and it's been absolutely excellent work, but you have to know that level to a few percent to do anything significant. Our result does not involve cleverness. It involves simply going far away from the sun and anything in the solar system, and we have made our measurements out at 57 AU away from the sun, and there is effectively the zodiacal light has completely vanished. So we simply taken that term off the table. So this is what we've used. That's the New Horizons spacecraft prior to its launch in 2006. And we use a small camera called LORI, which is the Long-Range Reconnaissance Imager. It is, that's interesting. I see that. Oh, okay, there. It took a while for that to show up. It's in the red circle. There's a port there which is closed at launch, and this provided all the high-resolution images of Pluto and Arrokoth. But this is the camera we're using. This is some of the details. It is a very small telescope. I own for my own use a 10-inch reflector I have at home. This is 8.2-inch, converting that to centimeters. It's a modest 1K by 1K CCD, which we bin with 4 arcsecond pixels. It has no filter. It's white light, so that's 0.4 to 0.9 microns. And the sensitivity for point sources is a whopping 20th magnitude. So, but it is in an incredibly dark place. So we have a few things that we have to worry about. And this is a laundry list of some of the things you think about, because you want to get the exact level of light precisely correct. So the first thing we were concerned about was the spacecraft shadow good? We are in still bright sunlight even beyond Pluto, and so you use the spacecraft to shield yourself from sunlight. And we asked the question, is the shadow good? It was. Negative means good in this case. Are thruster plumes scattering sunlight? The spacecraft is controlled by hydrazine thrusters, which you might worry make ice crystals. I won't go through all this exhaustively. One thing that I spent a lot of time worrying about, it's powered by several kilograms of plutonium-238, which makes a boatload of exotic gamma rays, and we have glass lenses for field flatteners right in front of the CCD. And so I was concerned if that was acting as a scintillator, producing Cherenkov radiation or fluorescence, and tracking all this down. That was not a concern. Lastly, I asked the PI and the project engineer if they put navigation lights on the spacecraft just for the hell of it, but that was not a concern. So that's what we have. This is where we make our measurements. This is a 100 micron image of the galaxy. And you can see what's aptly called infrared cirrus. There's dust all over the place. We want to avoid that, and we have to correct for it, as I'll explain in detail. So selecting fields, we exclude the zone around the galaxy, the galactic plane. We need to be in the shadows, so all of the angles must be 95 degrees away from the sun. And a little twist, we avoid the ecliptic, not because we are directly concerned with the zodiacal light ourselves, but because all the measurements of what's there are made from the Earth, and we didn't really trust it that much, so we wanted to stay away from where the dust was strongest. These are our fields. We had 16 fields for observations and some calibration thrown in. But basically, you can see that we are trying to get as close as we can to the galactic caps to make our measurements. These are the measurements that we had for 16 fields, and the x-axis is simply sorting them by their intensity. And you can see something right off. You may remember in the first slide that the galaxies were predicted to be around 6 or 7 nanowatts, and here our measurements are up at 20. And we also have, you see, quite a bit of scatter. We get almost up to 35. But we have a little bit of work to do. We see plenty of other things besides galaxy lights, and here's the things that you have to think about. You have stars below the detection limit that you have to take care of. There's a little H-alpha emission. The telescope accepts starlight from wide angles outside the field of view. We can measure this when we're close to the sun, so we actually know what the intensity is, but we are very sensitive to scattered light several degrees away from our optical axis into the telescope. We also, of course, want to know what we expect for the integrated galaxy light. We remove bright galaxies from our image. We have to put them back in for the integral, but we have to also understand what is, again, below our detection limit. So there are many things to take care of, and then one big term is what's called diffuse galactic light, which I will detail shortly. So a lot of these things are known, and this is probably the same thing Simon Driver and Saldana Lopez went through. For galaxies, we use the Cosmos galaxy counts. We have magnitude-dependent SEDs, or color-dependent SEDs, to integrate up what we expect for the galaxy light. We have trilegal for the faint stars that were below our detection limit. Some histograms over there. We do use surveys to account for the bright galaxies in our field, and that's when we add that to the average background. That's the red histogram, and there's some scatter there. The blue histogram are our various fields and the faint galaxy light. The thing that we sweated over for a lot of effort is understanding the diffuse galactic light. So you saw all the infrared cirrus. That scatters starlight. Okay, so that's going to make a background which we're still vulnerable to. And we are going to use the thermal emission of the dust to detect the presence of dust and remove it from our total light level. And I should say this is something that we sort of flubbed, and I can explain why in exquisite detail for our first two papers. Our last paper, where we had much more information, we revised this correction. So the way we do this is a self-calibration. You get your total sky level, and that's up there. You take off all the terms you know about, except for what you expect from dust in the galaxy, that's the DGL. And the plus means anything else that you didn't know about that's left over. And you expect a relationship between the scattered light level in the optical and the far infrared thermal radiation, and that's a calibration. And as they've posted it there, you see actually the intercept is negative, and so you have to take off the cosmic far infrared background, and effectively you're looking for an intercept, which is the stuff that you don't know about. And here is our DGL indicator. We use two colors, or two bands, 550 microns from Planck and 350 microns from Planck. And the reason we do that is because the dust varies in temperature, so you don't get a constant relation for any single band, but using two different bands allows us to put in a term for variable temperature among the fields. The points there are science fields in blue, and we had a special sequence where we went to more dust than we wanted to use for our direct science observations to determine this relationship. And this has worked very well. So we are taking out the scattered light from the Milky Way with this empirical relationship. And so I go back to the points which we showed. Now I'm going to add all of this up, and that's what we get. The integrated galaxy light, the faint light, we've taken out the bright galaxies, is in blue, and you see that's about a third of the signal. The scattered light, okay, from just the construction of the camera, is the gold color, and then DGL, scattered light from the Milky Way, is the beige color, and then green is the faint starlight left in the field. So there you can see that the total tracks very nicely the run, and we have only a small bit of unexplained light left. None of the bars actually hit the total measurement. I should say, though, in this business, everything is essentially entirely systematic errors. So we can't average these together. So the fact that this is common does not mean that this has high significance. For significance, we go through all of our fields and we do a Monte Carlo thing where we put in all the random error terms, we put in the systematic terms for all the fields. One of the things we do, since we're doing a self-calibration, we roll the dice 10,000 times and we rebuild the DGL far infrared relationship every time. Because that's calibrated from the data, we have to include that as part of the Monte Carlo thing. Then we compute the field for each, or the optical background from each field, and we compute the residual once we have known galaxies, and we get these two histograms. The first is the total signal. As I said, the gray shaded there is what you expect from all the light from galaxies, and there we put the bright galaxies back in. And then when we take that term off, this is our anomaly, which is at the 2 nanowatt level, and that goes to the conclusion, or actually here, let me show the total. I'm getting a little too quick here. So this is a review then of the first graph I showed, now with the observations made from New Horizons, and I'm going to zoom into that. And so the 90 NH21 was a first estimate made from archival observations. NH22 was the first attempt to do one field in our survey of 16 fields, and that's where we got the DGL wrong, and we revised it, and that's now the darker gray with the wider error bars. And our answer is in the black. That's the result from our 16 surveys. Subsequently, there has been a great improvement in the quality of analysis with the very high energy gamma rays. The SteveCat result is a result with no assumptions at all about what the gamma ray spectral energy or the optical spectral energy distribution is, but recovers a highly accurate measure. And the result is that we all pretty much agree. So there's the result. We have a little bit of anomaly, but it is not significantly different from the result that the total level is contributed entirely by external galaxies. So we have no particular need for exotic or an unknown source of light. We do have a little bit of room statistically to allow for things that are outside of galaxies, stars scattered out in faint low surface brightness galaxies. But for the first time ever, at high significance, all three measurements, census, very high energy gamma rays, and direct detections of the optical photons have converged effectively to the same answer. So this is where we are. And I'll stop there.
Signal was larger in the brighter. So the non-EVO signal mostly reached your measurements in fainter fields. It was later was larger in the brighter fields. Maybe.
I don't know.
I think there are some.
I mean, no, I don't think anything's compelling there. Well, what we did several images for each field, if that's what you're asking. We did. No, different. No, there's no term for variability at all with this. No, we pointed and we shot off a bunch of exposures and went to the next field. We assumed that this was all static. So DGL, do you mean DGL? Okay, so you have dust, that's the infrared cirrus, and just as you can see cirrus in the daytime sky from scattered light, it scatters light coming out of the Milky Way itself. And so our measurement of that is to do the separate thermal emission from the dust at very far infrared wavelengths, okay, so that gives you the dust mass. What is the relationship? That's independent data from Planck. And so what is the relationship between the infrared emission and the scattered light? That now is an empirical correlation, which we determined experimentally as part of our survey. Okay, and I have to say, I have to run, unfortunately, so this has been great, and I'm going to beat a hasty retreat. So.